Yes, I have one. Right. Good morning once again. I would need to quickly give a background to what happened on Friday. We realized that the lecture hours seem to be exceeding what it should be. So it appears you were doing CHM 101, 102, beg your pardon, 5 times. But in fact, it shouldn't be. So apologies, I couldn't communicate ahead, but we realized that while I was discussing with the coordinator, and so the plan is to adjust that. So going forward, our lectures will now be Monday 8 a.m., Tuesday 9 a.m. That's for section 102, sorry. Wednesday 8 a.m. and Thursday 9 a.m. Okay, so the Friday slot will no longer be necessary. Now, I'm sure you are all aware you've been subdivided into tutorial groups. So we expect that you would go and join the tutorial groups. Okay, so within those groups, if it is not a whole department together, it means you need to have a rep for that group. If it is the whole department, then I'm sure you have a class rep already for the department. But if it is not, let's say one department is divided into 2 or 3 because of your size, then you need to quickly appoint people to be in charge so that you can link up with the lecturers to have that tutorial. Now, the time on the timetable may not work either for you or for the instructor. So you need to work on some sort of arrangement that clears both sides. Okay, so please ensure you participate in the tutorial groups. All right, so we last week started the discussion on isomerism, and if I could quickly remind us of what we did. We said that on the one hand, we have constitutional isomers, okay, and that constitutional isomers could, in fact, simply be looked at as cases where you have the same atoms, but the way they are put together is different, okay? So we said under that, you can have, under constitutional isomerism, you can have what we label as a subgroup, functional group isomerism, skeletal isomerism, or positional isomerism, okay? And I try to explain what the difference between those are, okay? Again, this is one of the essence of going for tutorial groups, because there you would see questions to practice. I hope you all have the tutorial manuals now, okay? The tutorial manual is part of your practical package, the one you get to. You have tutorial manual there. Please don't wait till you go for tutorial class to begin to attempt the questions. You've bought it, it's your material, and so you are supposed to actually be attempting those questions so that the tutorial classes then are used to tackle the areas where you still have challenge. Maybe you solve the question you understand, rather than trying to solve each question from number 1. Okay, so you see questions on this all in the tutorials. Then went on from constitutional isomerism to look at stereochemical isomerism. And I said with stereoisomers, which is the name we call these types of isomers, you have a system where the constitution is actually the same. So the difference is not in the constitution. The difference in the constitution is to be referred to as the constitutional isomer. Okay, but this is not a case of difference in constitution, rather a difference of arrangement in space. And of course, when we talk about space, you know that takes us straight into the basic understanding of three-dimensional shapes and diagrams and imagery. I then said that, okay, under stereochemical isomers, that we have two different classes. And under the two different classes, I said the first one is with respect to rotation about a bond. Okay. And under that, I said we have two types again. The first is conformational isomers, or what we refer to as conformational isomerism. Okay. And under this, I try to explain that basically we are looking at changes, okay, in the actual bond. So what you have is you are looking at, for instance, in the example I started using later, but I needed an example to be able to help you understand this. I said if you look at ethane, for instance, and you arrange, so you know ethane has 2 carbon atoms, each carbon having 3 hydrogen atoms. I said there's a way we can arrange, if you hold a model of ethane, there's a way you can arrange the 3 hydrogen atoms such that they completely mirror or they block the 3 hydrogen atoms on the second carbon atom. And that means you are looking through the carbon-carbon bond. Now, once you have that in place, we say if you begin to rotate, you have to keep one of the carbons constant and rotate the other one. If you begin to rotate the other carbon, that you begin to have changes in the, type of conformation that you end up with. So we said those different possible structures are called conformers. Okay. And when we analyze the energy associated with a molecule, okay, as it undergoes this type of rotation, okay, we are looking at each of the different conformations we come up with, you end up with what is called conformational analysis. I then said that, of course, in addition to the other types of representation of organic molecules that we had considered earlier, that there's also something called the Newman projection. Okay, the Newman projection essentially is derived from the Sawhorse projection. So I said on this slide that the 2 images on the left, the 2 structures on the left, actually are examples of Sawhorse structure. Okay, these 2, okay, are Sawhorse structures. Okay, in other words, if you develop a typical what we call ball and stick imagery, or a typical model of this structure, this is actually what it will look like. So you have those 2 representing the Sawhorse structures or projections, and then on the right we have what we call the Newman projection. So if we look, and that's where I'm really going to be starting today's core explanations from. So if I were to be viewing from this side, suppose, sorry, there is sorry, I need to erase part of that. Just a minute. For some reason, my eraser isn't working right now. But it's fine. I'll just restart that again to make it easier. So essentially, what I want to explain. So yes, it wasn't clicking. That will always all. Okay. So if you have an eye at this position, all right, and the eye is looking at that structure, okay. Now remember, we're looking through the carbon-carbon bond. Okay, don't forget that at the center on this position where those lines meet, I have a carbon there and I have another carbon there. Okay, so if we're looking at those carbon centers, we're looking at those carbon centers, that in the way it is drawn in the staggered conformation, okay, we said that is called staggered. In that staggered conformation, the hydrogen directly above our front carbon, okay, let's call that carbon 1, and we call the other one carbon 2. So the hydrogen just above carbon 1, okay, if you look at the 3 hydrogens on that carbon, they are the ones represented in this. So this is the Newman projection now representing that first image. So you see that for carbon 1, we have represented the 3 hydrogens as the hydrogens that are joining, meeting at the center point. So that one where I put the dot now is actually our carbon 1. Okay, so you see the 3 hydrogens connected to it. Now, from that carbon 1, okay, so the 3 hydrogens connected to it, everything is represented. You are looking at the carbon. So we are representing the image based on this particular, it's like what they call a projection view. Okay, you're looking at it from this particular projection, okay, from a particular angle. Now, if you then begin to look at the carbon at the back, remember that carbon 1 is blocking carbon 2 to the observer. Okay, carbon 1 is directly in front of carbon 2, it's a straight line. So it means that you are not actually seeing carbon 2. So carbon 2 is represented by the circle. Okay, that circle represents carbon 2. Okay, so remember, we're seeing carbon 1, you can see the 3 hydrogens connected to carbon 1, but carbon 2 is the one at the back represented by that circle. Now, that carbon has 3 hydrogens as well, but the 3 hydrogens on the carbon 2, okay, are not directly blocked by the 3 hydrogens on carbon 1. So if you look at it carefully, you realize that they are more or less in between, okay, in the spaces between the hydrogens on carbon 1. That's actually where you have the hydrogens on carbon 2. And that's why you see the representation such that you have that hydrogen there, if I will call it, okay, that's on carbon 2, that's on carbon 2, and that's on carbon 2. Now, what it means is that in the staggered conformation, okay, there is actually what is referred to as a dihedral angle, okay, between the hydrogen, carbon, 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 hydrogen bond. What I mean is that the hydrogen on carbon 1, okay, is not directly blocking the hydrogen on carbon 2. Now, whether it's blocking it or not, we generally have a way of representing that. We call it the dihedral angle, and I'll represent it on this first image, okay, by that. Now, that space, that angle between one hydrogen and the other hydrogen, but I need you to follow me carefully. The 2 hydrogens, this is not a triangle situation. The 2 hydrogens are on 2 different carbon atoms. So there's actually a line between those 2 hydrogens. However, we are looking at that bond angle all the same, okay? That the bond angle is actually between the first hydrogen on top here, okay, and carbon 1, and then the carbon-carbon bond, and then the carbon and the next hydrogen bond, okay? So that angle in between is, okay, a phase type of angle called a dihedral or a torsional angle, all right? And that angle in this case is actually 60 degrees, okay? So what it means is that, and I'm starting with staggered for a reason, because if you can understand the staggered, the eclipse is probably a bit easier to follow. So in this particular conformation that we call the staggered conformation, we have that difference in the positioning of the hydrogens. Now, if we rotate that through another 60-degree angle, so I said the first angle here is 60, 60 degrees. Sorry, my 60 degrees, okay? And it's the angle on any of the other positions as well anyway. So that 60-degree angle, if you rotate, so let's say what we did initially was, let's say we start from this position and we take it through another 60 degrees. So let's say we move clockwise, okay? And we move it through 60 degrees. If you move it through 60 degrees, then you realize that the hydrogen that is on carbon 2 will actually come behind respective hydrogens on carbon 1. Okay, and so that brings us to the eclipsed conformation. Okay, and in the eclipsed conformation, what we are seeing now is that the hydrogens on carbon 2, again, to do this and do this correctly, you must keep carbon 1 constant. Or maybe the correct way to put that is you must keep one of the carbons constant. You're only rotating one. You don't rotate the 2 carbons at the same time. So when we are looking at conformational analysis, we hold one of the carbons constant and we rotate the other. You can decide to rotate the one in front, you can decide to rotate the one behind. Okay, but whichever one you do, you must only rotate one. For illustrative purposes, I will keep using or rotating the one behind. Okay, I think that just makes it easy for you to follow. So if we rotate from that staggered conformation, we do a 60-degree rotation clockwise. Okay, when I say clockwise, you understand what I mean. The hydrogen, okay, I didn't number the hydrogen so we do not get confused, but you understand what I mean, that each of the hydrogens on carbon 2 would then be, now they'll be directly behind a hydrogen on carbon 1. Okay, now this new conformation is called the eclipsed conformation. Okay. All right. Let me give us the first code for the day. Okay, so the first code for today's attendance code is Y3BQZ. Y for Yale, 3, figure 3, B for ball, Q for quiet, and Z for zebra. Y3BQZ. Okay, so I'm told there's a bit of a delay, but I would like to be sure we got that. Okay, yes, so we got it. Okay, thank you. Well done. Okay, so I go back to the lecture. Sorry. So we have the staggered conformation, and I said rotate that 260 degrees, you go to the eclipse conformation. Okay, the eclipse conformation, again, if you look at the sawhorse diagram on the left, this is the eclipse conformation. Okay, and the first one we looked at was the staggered conformation. So if you look at even in this sawhorse diagram, you see that, okay, one hydrogen, the hydrogen here is more or less blocking the hydrogen there. Okay, so that results in the diagram we now have on the far right. Okay, that is this eclipsed conformation. So essentially, in ethane, okay, is as you begin to rotate the molecule, what you realize is that you have between what you could call 0 degrees and 60 degrees, between 60 and 120 degrees, you keep having eclipsed and staggered conformations. Okay, eclipsed and staggered conformation. So if you consider eclipsed to be 0 degrees, okay, if you rotate it to a 60-degree angle, you rotate, again, remember, you're only rotating carbon 2. You rotate carbon 2 through a 60-degree angle, it comes to give you a staggered conformation. Hold carbon 1 constant again, you rotate through another 60-degree angle, making 120 from the original position. It brings you back to an eclipsed conformation. Okay, so you keep having those two interchanges. And if you look at the energy diagram here, you realize that, and to make it easy or clearer, I'm only showing two hydrogens, okay, just the two hydrogens, starting from that position on top here, okay, as our 0 degree. If you rotate that through 60 degree, it comes to, okay, this new conformation. As you can see, that is staggered. So we're starting from eclipse to staggered, okay, and I'm saying the energy between the two is actually such that in the staggered conformation, okay, the molecule is actually lower in energy, okay. Well, if you think back, clearly you begin to realize that because those two hydrogen atoms are now farther apart. Remember that lights will repel. Okay, so when you have two hydrogen atoms that are closer, there is some measure of interaction, okay, between the two hydrogen atoms, such that they tend to repel each other. So in that eclipse conformation, you have some measure of repulsion happening as a result of the fact that two hydrogen atoms are next to each other or are close to each other. And then when it moves to 60-degree angle, that repulsion is lessened, that tension is relaxed. Okay, hence you have a difference in the energy of the two. Okay, so again, if you rotate through another 60-degree angle, it goes to give another eclipse conformation. But remember, the two hydrogens that were directly in front of each other before have moved, but hydrogen is hydrogen. Okay, so there's still another hydrogen in front. You still have that eclipse. Remember, eclipse of the sun, it means one is blocking the other. That's the concept here. So we're using the word eclipse in terms of, okay, one molecule or atom is blocking the other. Okay, so so you have that kind of difference, and then you continue another 180, another 60 degrees brings us to 180 degrees, and so on and so forth till you get to 360 degrees. So this is showing the kind of difference in energy as we move the molecule from rotating from 0 through 360 degrees. So I just, everything I have just explained is what you have now on this slide. So essentially, remember that a staggered conformation is more stable than an eclipse conformation, okay? Because the staggered conformation maximizes the separation of electron pair, okay, in the molecule. So, like I said, likes will repel. The electron pair, there's more repulsion when you have them in the eclipse conformation compared to the staggered conformation. So, in the staggered conformation, there's less repulsion and therefore more stability. You understand? Now, so we've just described ethane. Okay, ethane is CH3 joined to another CH3, essentially. Now we take the discussion a step further and say, now consider the C2C3 bond in butane. Okay, remember that butane is 4-carbon system. Okay, and in quote, the middle carbons are C2 and C3. Okay, so it means that in butane, if you would write it out, let me just go a bit further to show. Okay, so this is what butane will look like. Okay, if you see the structure I have on this slide, just shows what the butane molecule looks like. So we are looking at carbon 2. If we say carbon 2 is the one in front, and then carbon 3 is the one behind. The idea is that it means then that you have one methyl group on each of those carbons, and two hydrogens on each of the carbons as well. Okay, so it will now be methyl HH. Okay, so let's just have that at the back of our minds. All right, so if we consider that C2C3 bond, in this case, there are 6 important conformations. Remember, as we do that rotation, every angle every single angle difference, in fact, every point something degree difference is a new conformation. But what I'm trying to help you see is that of those conformations, there are some that we consider to be important because they bring us to some sort of energy minima. Okay, so in the case of ethane, we said the staggered and the eclipse conformations really were the two important ones, of course, and you get those at 60-degree rotation variations. But with butane, we're saying that there are 6 such important conformations. Okay, now in one case, the 2 methyl groups, okay, have what we call a gauche conformation. Okay, in the other, the 2 methyl groups have an anti-conformation. Now remember I said you have 2 methyl groups on the and maybe I need to come here to try and illustrate where we are going. We already have the background, so most of the things I have on those slides are just trying to explain in detail what I'm going to quickly show you now. So you have, let's start with our 0 degree to be this structure on the left. Okay, between, you have a case where the 2 methyls, okay, now are directly blocking or mirroring each other. Okay, so we say, of course, that's remember eclipse definition. That's like, okay, bringing us into that type of eclipse position. But in this case, it's a methyl group on those 2 positions, and the others are hydrogen, similar to ethane. Now we're saying that there is this conformation where we have the 2 methyl groups blocking each other. So you have that as a form of eclipse, but like I said, it is called slightly differently called the gauche. Now, if you rotate through 60 degrees, I'm sure by now we can follow the diagram a bit better. 60 degrees, it brings us to this situation where we have 1 methyl now. Okay, as you can see, the methyl on the carbon at the back. Remember, we're looking at C2C3 bond now. So the methyl on carbon 3 essentially is now at what we call a torsional angle or dihedral angle of 60 degrees. Okay, as you can see, the 2 methyl groups, they are 60 degrees from each other. At least looking at it in 2-dimensional representation. Now, if you rotate that to 60 degrees again, now, but you will see that unlike the case of ethane, where the rise and fall were basically coming to or from the same energy level, in this case, there are differences. And you will see that the position you have after this first 60-degree rotation is not the same as the position you have by the time we get to what represents 180 degrees. Okay? And what I mean is that in terms of the energy now, okay, look at the energy there and the energy here, energy levels are not the same. In that of ethane, as we were rotating, it was coming from a particular energy level, coming to, and then a staggered eclipse on top, staggered below, and it was rising and falling to the same value. But in this case, it's different, okay? And this 180-degree position is the conformation referred to as the anti. Okay, the first one on the left, where we started from at 0 degree, is the gauche. Okay, now, but again, you can see that in the anti-conformation, the 2 methyl groups are 180 degrees from each other. Okay, that is, the dihedral angle or the torsional angle here is 180 degrees. The dihedral angle, torsional angle for the gauche is 0. Okay, but of course, as you do the rotation, okay, from 60 degrees to 120 degrees, you see that it comes to another position where the methyl is not blocking a methyl, but a methyl is blocking hydrogen. The other methyl is also blocked by another hydrogen. So in this case, you are seeing that as you rotate through 60 degrees, you are getting conformations that are in a sense different from what we had for ethane, because in ethane you only had hydrogen, okay, around the carbon atoms that were in the middle. But in this case, because we have methyl and hydrogen, okay, so you are having differences. Now those differences also lead to slight variation from the case of ethane that we considered earlier. Okay, as you can see, when you go from the 60-degree position, remember this is 60 degrees, okay, and 120 degrees is the structure we have there. Okay, so I hope you're able to follow how we look at it on the x-axis against the actual shape of the curve. Okay, so at 120 degrees, we are looking at this structure, okay, where we have a methyl blocking a hydrogen, or hydrogen blocking a methyl, okay, different from where we started from at 0 degrees. And then you rotate that through 60 degrees, it comes to the anti-conformation. Through another 60 degrees takes us to, okay, if you look at this at 120 and at 240, you see that the two structures basically involve methyl mirroring a hydrogen, okay? And so the two of them relatively are similar if you look at them carefully. And that's why you see that the energy value at those two positions are actually the same, okay? Because you have a methyl shielding or blocking a hydrogen, methyl being blocked by a hydrogen. Same thing on the two, at those two angles. And therefore, they have the same energy value. Same thing if you look at the structure at 60 degrees and the structure at 360 degrees, okay? You see that the two structures, okay, also appear similar, okay? Okay, and so again, they have the same energy value, okay? Of course, when you get to 360, it's more or less that of 0, but that is, so if I now quickly go back, all right, I can give you the second. The second code for today is N for Nigeria, 2, Q for quiet, Y for Yale, T for top. N2Q, YT. N2Q, YT. Yes, that is correct. Okay. You need to pay some attention to be able to follow. Essentially, I'm trying to explain how we use, okay, we're looking at isomerism quite all right, but we're trying to explain how the changes in the carbon-carbon bond is responsible for the types of conformers that we have for these molecules, okay? Now, so I said you have the gauche conformation. Okay, sorry. I'm first looking at the 2 methyl groups, yes, have a gauche conformation. In the other, the 2 methyl groups have an anti-conformation. Okay, sorry. In the gauche conformation, the torsional angle between the 2 methyl groups is 60 degrees, and for the anti-conformation, the torsional angle is 180 degrees. There's an energy difference between the anti and the gauche conformation. The anti is more stable than the gauche conformation, okay? Okay, now the real reason why we have this kind of variation, okay, is because there is what we call van der Waals strain, okay, between these groups. Van der Waals strain, of course, and as you continue to read, I try to explain some of these concepts. Because the two methyl groups, the closer they are, then you have, as you would expect, higher repulsion. Now, apart from just the electronic repulsion that you have for hydrogen, in the case of a methyl group, the methyl group has a radii. Okay, so as a result of that radii, you would have what we now describe as the Van der Waals strain. Okay, and that simply means that the size of this group really, in a sense, affects the size of the other group. So if you have two big groups near each other, there's bound to be repulsion. Okay, not just in terms of electronic alone, but even as a result of the size. So as a result of these sizes, you have, and that's why I try to indicate what the Van der Waals, the differences in the Van der Waals radii, okay, for hydrogen atom and that of a methyl group. So you see that as a result of this difference, comparing the conformation in butane with that of ethane, you are bound to have, you see, higher level of distortion, level of strain, okay? And so in this case, you'd realize that that strain is less pronounced in the anti-conformation, okay? And then, so this Van der Waals strain is called steric strain, and is really as a result of groups and result of the sizes of those groups as they come close to each other. So this slide just tries to build on what I had explained earlier. But in simple terms, if the two groups are close to each other and they have considerable size, you would have a measure of repulsion. Okay, and this repulsion is what we refer to as the Van der Waals or the steric strain. All right, so we said, so butane has two distinct, what you could refer to as staggered conformations. It also has two distinct eclipsed conformations. Okay, in one of those eclipsed conformations, the two methyl groups actually mirror each other. I said that's where we are starting from, like our 0-degree position. Okay, in the second, the methyl groups eclipse a hydrogen. Okay, I already showed that when you get to 120-degree rotation, you are looking at a case where the methyl is now blocking a hydrogen, not methyl blocking methyl again. Remember, we are choosing to start with methyl blocking methyl as our 0 position. Okay, now, yes, in both cases, we have eclipse bonds, okay, and there's bound to be torsional strain. So, however, the methyl-methyl eclipse conformation significantly affects the Van der Waals strain, okay? So, at a level, we'll see that there is greater strain arising from larger methyl groups, okay, compared to what we have with ordinary electron-electron repulsion. So if you look at the same image I've been using to explain all along, so I'm saying that gauche conformations 2 and 4, as we have in this slide. So 2 now is this, and yes, so we have this here, and we have the other there. Okay, well, in this case, sorry, 2 and 6, sorry, it's 2 and 6, the Thesis is not 2 and 4, 2 and 6. So if you look at what you have on this left and on this right, those two structures actually are examples of conformational stereoisomers. Okay, but the important thing is to realize that starting from that eclipse position on the left, that we come through, as you rotate through 60 degrees, you come through this different angular rotation, leading to us to new conformations, and those conformations have different energies. Okay, we are basically rotating through 60 degrees. We're rotating through, as you rotate the back carbon through 60 degrees, it changes, coming to, and as you can see, the torsional angle there already shows us the angle of variation. From 0 to 60 to 120 to 180 is simply a 60-degree variation. But most important is for you to understand that the anti-conformation in the middle at 180 degrees is the most stable conformation. It's the most stable. You can see in terms of energy, it is the one with the lowest energy. Remember, the lower the energy, the higher the stability. So it is the most stable conformation, while the eclipse conformation, where we have the methyl blocking the methyl, is actually the least stable conformation. All right, so all of that is simply explaining the case of, remember we said you can have conformational isomers as a subtype of where we have a rotation of carbon-carbon bond. Now, the B part of rotation of a carbon-carbon bond is configurational isomers. Okay, configurational isomers. Now, this occurs, this one you are probably familiar with. This occurs when there are identical substituents on a double bond or a ring. Okay, and this is normally where we use the terminology cis and trans. Okay, the important thing here is to realize that if you look at the structure on the top left hand side, well, based on where I do the structures now, the one there, you have cis 1,2-dichloroethene, and essentially the difference between that cis and the trans is that it's as if one of the chloro groups has been moved through a particular angle to give what is now the trans. Okay, and I'm saying in this case you have it's like saying we had to rotate through that bond. Okay, so you rotate through the bond and turn one of the chlorine in the opposite direction. That will lead to the product we have on the right. So again, this is a type of isomerism that you find in either compounds with double bond or ring systems. Now, while the two chlorines are facing what you could say facing up in the cis conformation, in the trans, one is facing up, one is facing down. Okay, in other words, the directions of the two chloroatoms are different if you consider the cis and the trans. Of course, the two chloro could also be facing down for them to be cis. Okay, here we have drawn it in such a way that they are both facing up, but they could also be both facing down. Again, remember, we are concerned about how these things appear, how they are arranged in space. Okay, so up, down, in, out are the kind of terms we're definitely going to be interested in. But whereas with the trans, they are on opposite sides, and so it's trans. And I know you have definitely come across cis and trans before now. However, for the cyclic system, you have an example here, cis 1,2-dimethyl cyclopentane. Remember I said if we use the wedged bond, okay, the deep lines, okay, it means that the two lines, okay, are facing the the writer or the reader. Okay, so the two of them are facing you, meaning they're in the same direction. Okay, again, that represents cis. Okay, but in the trans on the right hand side here, for that cyclic structure, you can see that one is facing you, the other is pointing away from. Okay, so again, that reflects trans. Okay, for the cis, remember, they could both be facing you, they could both be pointing away from you. So you could have the hashed wedge bond on both carbon atoms. That is, it could be the broken lines for the two cases. Okay, and it will still be cis 1,2-dichloropentane. But for the trans, one must be facing you, the other must be pointing away from. So the direction definitely must be different for it to be a trans trans isomer. Okay. Okay. Also to mention that configurational isomers have different physical properties. All right. So the third code for today is 847 TU. 847 TU. 847 figures, T for top, U for umbrella. Okay. Just want to be sure. All right, so that's one. A few of you already have it. Okay. All right, so that's configurational isomers. Now, remember, the first thing we started with was saying with respect to rotation about a bond in terms of the two main classes of stereochemical isomers. And we looked at one, constitutional isomerism, conformational isomerism, where we have conformers, and we have looked at the second one as configurational isomerism, where we have conformers. Now, we can also have with respect to rotation, that's the second type now under stereochemical isomerism, with respect to reflection in a mirror. With respect to reflection in a mirror. Now, under this, we have two types. A is the enantiomers. Sorry, that should be this, not those. This type of isomerism is only found in compounds whose molecules are chiral. Chirality is a term I need to quickly explain. Some may not have come across it. I'm sure some of you have. A chiral molecule is one that has no plane of symmetry. Okay, and so if you look at the hypothetical structure I have drawn on that slide, with A, B, C, D serving as substituents to the middle atom C with carbon normally. If A, B, C, D are different, then you have a molecule that is chiral, a molecule that has no plane of symmetry. But if any of A, B, C, D are similar, so whether it's A, B that are the same, so instead of A, B, it's now maybe AA, for instance, AACD, then you still have a plane of symmetry. But when there's no plane of symmetry, when the four substituents A, B, C, D are all different, then the molecule is said to be chiral. Okay. Now, the carbon that is carrying the substituents is known as the chiral center. Okay, the chiral or stereogenic center. Okay, so that middle carbon, the carbon carrying it, is called the chiral center. Now, please note that chirality is only possible when you have an sp3 hybridized carbon center. Okay, you would not have chirality where you have a double bond, for instance, because at a double bond, remember that the hybridization for the carbon that is a double bonded carbon is not sp3, it's sp2. Okay, or where you have a triple bond, okay, and so on and so forth. You have a carbonyl. Okay, so the important thing is to remember that chirality is only possible when you have an sp3 hybridized carbon center. So, for instance, in the structure of lactic acid that I have on this slide, which carbon is chiral? Let me number it so that you can quickly just give me the answer by numbering. Let's say that carbon there is carbon 1, this carbon here is carbon 2, and this carbon here is carbon 3. So which carbon center is chiral? Which carbon center has 4 different substituents? Which carbon center has 4 different substituents? I'm waiting for your responses in the comment section. Which carbon center has 4 different substituents? In other words, which one is chiral? Okay, I see 1, I see 2. All right, so I need to clarify between carbon 1 and 2. Okay, sorry, I see there are a few questions about some of the concepts I explained earlier. There's physical class. Someone said there's no physical class. The physical class is what we call the tutorial classes. Okay, again, the way CHM, and you did this during CHM 101, so you know already. So we have the tutorial classes that run. All I've said is make sure your class reps connect with the lecturers or the instructors so that you can have those tutorial classes. That is the physical class. Okay, and what I'm doing here to be impossible. Again, you know, we can't have all of you in one room. You are much more than we have any lecture theater for. That's why we are using this method. All right, so please, if there's anything that is unclear, you can ask the instructors in physical class. All right. Now, 1, 2, 3. Some people say carbon 1, some people say carbon 2. Now, carbon 1, look at it carefully, is not sp3 hybridized. Okay? Okay, look at carbon 1 very well. Carbon 1 is not sp3 hybridized. Okay? Carbon 1 actually is sp2 hybridized. Therefore, it cannot be carbon 1. Okay? Carbon 2, on the other hand, has a methyl group, has a carboxylic acid group as the next substituent, also has an OH. Remember, I said when we write structures like this, you must remember that there's the valency of that carbon is not satisfied except you have a hydrogen there. So there must definitely be a hydrogen. I mean, remember, I tried to explain the way Amanda will write organic formulas. Okay, and in this case, clearly the hydrogen, the last member of that structure, is not showing directly. Okay, so in fact you have a hydrogen there, and so it is one substituent is the COOH, the second substituent is the OH, the third substituent is the methyl, and the fourth substituent is hydrogen. So this carbon here, carbon 2 here, is actually a chiral carbon center, okay, in lactic acid. Okay, and the point is that the non-superimposable mirror images. So what I mean by non-superimposable mirror images is once we have established that that structure, that lactic acid has a chiral center, if we are going to represent lactic acid, okay, in the 3-dimensional representation, you see what I have on this. At this position, that structure, if you look at it carefully, it is the same structure you have above. Okay, what I have there is the COH as a substituent, the OH as another substituent, the CH3 as a substituent, and the hydrogen now showing in the 3-dimensional representation. Okay, but you will notice that the way we have drawn it, the hydrogen is pointing towards the observer, and the methyl is pointing away in that first structure. Okay, now if you go, when we say non-superposable mirror image, that means we're dealing with a mirror. Okay, now if what we have is placed in front of the mirror, okay, what you will see on the right hand side, so you remember I'm starting with the image on the left. Now the mirror is the line there. Okay, that's the mirror. Now, what I have in front of the mirror is the image. Okay, so it's like you standing in front of the mirror, obviously you'll be seeing your image. Now, in that image, what we're left with is you'll see that the part that is on the right, okay, in the original structure on the left, will now be on the left in the new structure in the mirror. Sorry, I hope I hope I'm clear. What I mean is, if you look at it, I mean, and it's you can use anything to illustrate this. If you put a mirror in front, what you will see is, you know, the CH3 that was on the right in the original structure will appear on the left in the image that will appear in the mirror. Okay, so exactly the way I've drawn it on the left-hand side, what you have on the right-hand side will be the mirror image. Okay, now these two structures are mirror images of one another. But if you look at them carefully, there's no way we can place, if I call this A, there's no way we can place A on top of B. Exactly. What that means is that it's like your left and your right hand. There's no way you can rotate your left hand to exactly, you know, they are mirror images of one another. Okay, if you place this in front of a mirror, you will see the other hand. Okay, but they are not the same. And what I mean is that there's no way you can twist your hand for this left hand to suddenly appear like the right hand. Okay, there's no way you can twist your left hand for the left hand to be facing that side. Okay, and the thumb will still be up. Okay, if you want it to face that side, the thumb will be facing that. There's no way you can. So those are what we call you know, enantiomers. When you have something that they look similar, they almost look alike, but you cannot actually superimpose one on the other. So non-superimposable mirror images are called enantiomers. Okay, and the structure I've given you here, lactic acid, is a typical example of enantiomers. Okay, and like I said, e.g., your left hand and your right hand, or your pair of socks or your pair of gloves. Okay, some that are made to be specific, you realize that you cannot rotate them on top of each other. Okay, enantiomers have similar physical properties such as boiling point, melting point, solubility, and so on. Okay, it's already time, and I guess some of you might have another class, so I would stop here for today. Remember, we have gone from rotation about a bond. Now we are looking at cases of not just rotation now, but we're looking at reflection, okay, in a mirror. Okay, and the first example considered are enantiomers. Thank you so much for joining today's class. I'll see you tomorrow at 9 a.m.
Good morning. This morning, once again, go straight to where my colleague stopped with you last meeting. Now he was able to lead you into the aspect
That started conformation.
of the aspect.
Lead you into the aspect.
Ah.
That started conformation.
Okay. In my hand, touches inside. Yes. I'm sorry, there is this interruption in the arrangement of slide. Now we want to start with this, please. So my colleague told me he has taken you through some of the previous slides. But nevertheless, if you have any challenge or problem, let me know. Like I've given you the freedom, come directly to the atmospheric lab for further or details information. So we want to see this as a new development in looking at forces. You see something like a block placed on the table. And when you see this, it simply means there are forces, just like the beginning of this course, the introductory aspect, forces in nature. So there is normal force, F subject N, which the table is giving to the block or any substance placed on it. The second force, F of G, which you are familiar with as gravitational force, now pulling the table towards the earth gravity. That's called it F small letter G. Don't forget that the block itself has its own weight. And you should remember from your O level that weight is equivalent to what? Force. So F is equal to what? mg. So mg is still your force. But G in this case will now be taken as your gravitation. So in other words, there are some forces. We call them normal force. Then there are other ones which are reactional force, which is due to this table. So we have to consider that assuming the table surface is smooth, then that reactional force becomes zero. But if the surface of the table is rough, then you have the table also reacts to the block on which block put on the table. So this diagram at this side is to depict the nature of the force acting on the body. So the body is represented with that black spot. And so X has its own direction, so that when we begin to navigate the force, we look at the force in line with the direction in which it flows, because force, as you have been taught, is a vector quantity. So direction to it is very important, particularly in this particular aspect. So take note of that, guys. So we can, for the second aspect, forces Fg and F of n are the only two forces on the block here, and they are both vertical. That is, I'm dealing with vertical forces now. You could remember the second law of motion, which you call Newton's second law from your O level, for positive upward forces. Now I'm considering the y-axis from your mathematics as my vertical. So if it is x-axis, I'm talking about the horizontal now. Now I'm linking your mathematics with physics. So net force, which I'm representing with F net along the y-axis, is equal to MA. Your acceleration is also involved in direction. That's why it's also a vector quantity. So that is why A of y is defined in this equation. So for somebody who want to give me the best equation for this aspect, you can now say F of n minus F of g equals to M of AY. And of course, F of g, like I said, is like the force of gravity, which is like mg. So I'm replacing my F of g with M of g equals your AMA. So it's therefore easier to say the net force, F of n, is mg plus ma, which can be summarized when you put a bracket m into g plus a of y. So take note of that. Now, force application on cord. This is equally very important. A cord is often said to be massless and unstretchable. Take note of that, because when you get to another higher class, that system will change, or that idea will change, because we have some elastic and inelastic body. So, but for your level now, a cord will be massless. That is, we are not attaching mass value to the length of the cord given to you in the exam. And two, that it's non-stretchable simply means you can't increase the length. If it is 10 grams, it remains. So if it is 20 grams, it remains 20 grams. You can't change to 15 grams. So the cord then exists only as a connection between two bodies. Take note, it pulls on both bodies with the same force, magnitude. And so we now talk about tension because it has to do with the rope. So the stress on it is what is described as tension on the rope. So instead of using F now, I'm using T. But you have in your mind that T is indirectly representing the pull on the cord, which is the tension. So the cord pulls taut is under tension. So if its mass is negligible, the cord pulls on the body and the hand with force. Even if the cord runs around a massless, frictionless pulley, as in the figure below, the rule is still enforced. So you can see this simple example. Here I'm giving you the diagram to explain three things. You can see the hand holding the rope. And T capital here represents the tension. And the arrow on top of the T indicates the direction on which the force or the tension is applied. So see the other end of the table. There's what we call pulley there. Pulley, you must have been so familiar with pulley from your secondary school in physics practical. That is, if you happen to attend good school with practical class. But notwithstanding, you can easily understand, as I explained, that rope is tied to the block and the other end passes through the pulley. The pulley is just to give it a free move. And so that's why no special tension is attached to the pulley. It's free to roll, and it's only helping us to move the block. In this case, we assume the forces at the two ends of the cord are equal in magnitude. How do you mean? When you apply equal force, listen to that, very important, because I can come up with a new question from that. When you apply equal force, but at the two ends of the block, what happened to the body? The body remains stationary, because equal force, or let me say forces at both ends, are equal. In other words, F is equal to 5 Newton at one end, F is equal to 5 Newton at the other end. And so pulling the body will cause the body to remain at rest. So F1 is equal to F2. So the body remains at rest. And that means your U, which is your velocity of the body, is equal to what? 0. So all other rules about equation and forces will follow. So if initially your F is equal to mg for the tension, look at the hand pulling the rope down. So you are the one enforcing a particular tension on the rope. And so the direction of the tension T is also important to us. Look at the arrow pointing upward. Somebody would have expected that your tension comes down. No. The tension will pull up, and that will manifest or be established in our equation later. But very importantly, you need to understand this diagram, that the force at the two ends of the cords are equal in magnitude. So the size must be equal before the body remains stationary. Now look at this one. There are two forces here, but with one pulley. So we are saying that the tension direction, which is the direction of the force, remain the same. Looking at the arrow, the hand is pulling the body but downward, while the force is acting upward, or the tension on the rope. So the tension on the load or the block is also acting upward because the body is being moved upward. So definitely the force acts on the body to pull it up. And so the other third force that we'll have considered is the one on the pulley, which remains zero. So we assume that the force on the pulley remains zero. Now, whenever two bodies interacts, the forces on the bodies from each other are equal in magnitude and opposite in direction. So as part of the usual question I put to you, I can ask you at any time that which of the following is correct about the body being pulled upward, assuming friction is zero or there is no friction. So meaning that you have to consider that as a priority. I hope this diagram is clear because we are going to come up with two questions from here. The first one will look at the block. The second will look at the direction of the force or the tensions on the body. Yes. The forces on B, which is the block, has the same magnitude as the forces on C with this diagram. So I'm now specifying or emphasizing, so to say, on the direction of these two bodies. The other one was vertical. Now we want to look at the motion of these bodies on the horizontal. Then don't forget that once a body is placed on another object, the nature of the object on which the body is placed is important to us. Is it a smooth surface? Is it a rough surface? So if it's a smooth surface, you forget about friction on the body. And that's what we call rho in your O level. But when the body or the surface is rough, then rho is not zero. So you have to be given the value, or you find the value once you know the force F and your mg on the other side. So my F of BC is pointing that side for B. The F of CB is pointing the other side for the body C. So I want to establish this, that F of BC will be equal to F of CB. And that is what we mean by equal magnitude. But when the direction change, look at F of BC, which was pointing the other side, suddenly change. So I now turn the arrow to the other one. Then because it is opposite in direction, the sign must change. just as you have been taught under collision, that when two bodies collides, the condition to be considered are two. Number one, you have the body fixed together or coalesces when they come together, or they separate immediately. So the same force is still on the body. But when the two bodies coalesces, then they have combined velocity, or what we call common velocity. But when the bodies separate after the collision, then they have different velocity. And so the momentum of each body will change. And so the same principle works here, because we can link your question to that same topic. So don't think we are going beyond the scheme. It's the same scheme. And this is university level. So take note, once the alteration is brought here on direction, then the sign will change. And that's why the idea of minus sign is seen here as minus of F for CB. So take note of that. Now block on table and block hanging. So this is to establish the principle of frictionless and body under friction. For a body placed on a table to slide, then there are conditions. Just a minute. Sorry, please. While we are listening to the explanation on block and the block suspension or hanging, I would like to dictate the first code, attendance code. So you listen. N capital, that's N8 BTU. N8 BTU. I repeat, N8 BTU. That's the first, take note of that. So I continue, please. Now I'm trying to explain the first table. On the first table, you notice there is no application of force. The table is free with mass M capital. But two, you have to look at the direction as indicated by the arrow. The arrow is pointing towards your right along the pulley, and you can see the arrow bend to show that the force is towards that M small letter hanging below with block H. So the first thing to do when you have two blocks is to understand the position of that block. Is the two block placed on the table or one is free? That's the first thing to do. Otherwise, you can't get the equation. And there are so many ways of changing the equation. That's the serious aspect of this topic. It's the only topic in physics that does not have stable equation. Others have constant and definite equation. So the equation will be derived depending on your understanding. It's very simple to understand. So that's why I'm taking my time to explain this. And simply, you have to know that we'll meet some questions on this topic so that you prepare your mind for that. So you need to understand it. You see what is put on the first table, frictionless surface. What do you understand by that? It means your mu, that is the friction on the table, is 0. In other words, it simply means that the surface is smooth. So the question may not tell you that, but when it is written that frictionless surface, that means your friction on the table is 0. So I won't recognize mu of R. Now capital R, as we have been taught in O-level class. Now the next thing to consider is to which of the direction is the table sliding. So you now look at the position of your arrow as the second thing to consider. Look at the direction of the arrow, which means the block is being moved towards your right. So the next thing, which is number 3 to consider, is which of the forces is pulling the body. And so that's the hanging block below. And this can be simply understood by the direction of the arrow pointing down on the hanging block, H capital. So it's easier to now deduce the equation, which means once the hanging body is moving that direction, the capital M block must follow. The simple idea now is, without anybody telling you, it suggests to you that the actual weight or the sum of the weight of the hanging block, H capital, is greater than the one on the table. That's why it moves. Then somebody can ask, what happens if it doesn't move? If it doesn't move, it means the sole weight, the absolute weight of the one on the block is greater than the one being hanged. In other words, that suggests to you that the table is not smooth. So there's a friction. That's why it doesn't follow. Simple knowledge, simple mathematics. So the capital letter, capital body, M capital, can only follow the smaller body if that surface is frictionless. 2, if the small letter M block is higher or greater than capital letter M block. Those 2 conditions clear. So it's now easier for me to deduce the equation by saying my mg, small letter m now, plus mu of capital R, that is for frictionless body, must be equal to m capital of A. God is enjoying his own normal acceleration. It's not G.O. Don't misinterpret that, because it's on the table. So you must understand between acceleration in a specific direction and acceleration under gravity. So the only body that is enjoying the gravitational rule is the one being hanged. But the one on the table is enjoying uniform acceleration. So it's small letter A, not G. So in my equation now, I must be careful in the symbol being used to substitute. It's just that it's not a theoretical exam. I mean, exam that you write and will mark your notes. So in objective, the one you guess is your own guess. You are the one to decide whether you are right or wrong. But at the same time, you will know whether you are right if you understand the subject. That's about the first figure. This figure is very important of figures because it explains everything about this topic. That's why I put the second one beside it. This second block, we can see. The first thing to ask myself or ask yourself, what's the difference between the first block and the second block? Yes, good, if I may ask you that question. What do you identify as the difference or differences between the first block and the second block? Good. Yes, that's what I want. I want your response. Now you can see it so clearly. Let's be a difference between the first block and the second block. Okay. Okay. So let me go back to the slide. I haven't seen your response. Now, this second block, you see the arrow pointing upward, another one pointing downward. Fn, upward, we call it normal force, which the table acts on the body placed on it. And the body placed on it has a mass. And that mass is capital letter M, different from the other mass, small letter. The second thing to understand, is there any other force? Yes, which is different from the first diagram or the first block. The second force is indicated by the arrow pointing downward. And in that case, they didn't put FA. The symbol or unit here is F of G of S, meaning that they are talking about the force pulling it across the surface. Sometimes some people call it frictional or dragging force. Because if the Fg of H is higher than Fg of S, the body will follow. And so the direction of the arrow showing tension T capital is already indicating the path and the motion of the block M capital. So this is a bit better, I won't say difficult, than the first diagram. Better in the sense that you need to be patient to understand the diagram. Otherwise, you won't be able to solve any problem in this type of equation. Somebody will ask, is there any force along the pulley? No, because we assume the force on the pulley is negligible, and that will be stated in your question. Otherwise, it becomes more complex for your level. So we assume at your level, the force being acted upon by the pulley becomes zero or negligible. That is to be ignored. So I can now estimate the number of forces in this case. So there are at least three forces to be examined on this block or diagram compared to the other two forces in the first diagram. The first one is the normal force, F of subject N, which is equal to M capital now, A small letter. A is because the body is placed on the table, so it's assumed it's moving on the horizontal direction. And there's a force being employed, so we don't have any problem with G. So gravity has nothing to do with this horizontal motion, so you don't include G. But mind you, the next force is shown by the arrow pointing downward. which is Fg sub to G of S, which means there's another frictional force, either frictional or non-frictional. F is F. The only difference is that the surface on which the body is acting. And good enough, the surface can be seen from the diagram. So that is represented with S capital. So the force on the surface here will involve gravity, because the direction is important to us. We believe that block placed on the table is acting downward. I mean, the pull is down, but the table acting down directly on the table. So there's no way we can ignore the gravity. So making on a single block capital letter M, I have discovered how many forces now? 2. Then the third one, which is very important, is the direction in which that T capital is going, tension. The tension on the rope is important. Tension is a force. And because the arrow is indicated, that makes it easier. So we have mu R. Mu is coefficient of kinetic friction or kinematic. The same. So meaning that that body is undergoing kinetic energy. There's an energy pulling or forcing the body towards that direction as shown. Therefore, we cannot ignore it. So the rope in this case carry that force, making 3 forces on a body. Now, I would now equate those 3 forces to the one acting at the other end of the pulley. Take note, at the end of the pulley, there is another block, but with small letter M. So all I'm after is to equate these 3 forces identified on the first block to the other forces now to be identified with small letter M on the block. And so that block is named as block H capital. And because it's block H capital, then it is easier for me to form another equation. It doesn't matter the number of equations you have in physics. All we're after is to resolve it. And more so, you'll be happier. The more the equation, the happier you become. So meaning that my tension is number 1, look at the direction. The weight now is number 2, look at the direction of the arrow. So I've identified 2 forces on the small letter block M. Good. I will now equate the equation or equate the equations, the forces in the right to the forces or number of forces at the other side. And so the equation is formed. So simply by looking at diagram, you can form your own equation. That's the only difference this topic has with any other topic in physics. It doesn't have a definite equation. You will form the equation, and the equation can only be formed by the way the material or the block is arranged, where it is placed, distance to where it is placed, the position of the body, the smoothness or roughness of the body. These are conditions that gives you the equation to be used, and it's very simple. So you just equate the first side of the equation to the other and find the unknown, because the unknown will come up so easily. Simple. That's about this block. If you have any question on this particular diagram, which I know you will have, I'm giving you the privilege that you will be attended to, but like you have been coming, you come in group, not just one person. Because the staff attending to you will not want to take just one student. So you look at your friend who have similar problems, maybe 3 or more, and come to atmospheric lab. only on Monday, like I've explained to others, and Thursday, and that will only be between 10 and 12. And you can only come before the test. Once the date of the test is announced, nobody must be seen around that office. So take note of the instruction. So I can now finally give you the summary of the block arrangement. The summary of the block arrangement, that is the way I put the blocks together. 1, the cord pulls to the right on sliding block S with a force of magnitude T capital. 2, the cord pulls upward on hanging block H. You know, the blocks have been named, with a force of the same magnitude T. This upward force keeps blocking H from falling freely. And take note of that condition. That's why the direction of that force is up, because it's assumed it's hanged and keep it upward or hanging. Otherwise, it will have fallen the moment it's released. There are other questions to be asked under that. Why is the body remain as it is? One of the conditions is that the rope is not extensible, it's not elastic. So there's no way it can change the length. So the length is constant. That's another way of putting the option there. Once you say the length of the rope is constant, it's telling you that it's not extensible. Number 3, earth pulls down on block S, that's gravitational pull. With gravitational force, F sub to G of S has a magnitude equal to M capital G. Don't forget that M capital is for the mass of the block on the table. So that assumption is very important. Otherwise, your equation will cancel out, and that will be fun. But what am I now pulling if there's no equation to solve? Okay. Finally, the block, the table pushes up on block S with a normal force F of N. So I've told you F substitute N is normal force, which is the force acting on the body placed on the table. And it's also assumed that the table for the first figure is frictionless, and it is written on the diagram. The second table is not frictionless. That's why you have another arrow pointing downward, representing that there is a friction on the table. In other words, that table is rough. And once it is rough, it generates friction on the body you are placed on it. So that friction needs to be found. And that is what made the other table with 3 equations, as I've explained. So with that, I think it will be convenient for you to round up for today. And may I dictate the last code for your attendance. XB 78W. XB 78W. X87BW. Thank you. Good morning. Okay, sir. Sorry, the third code. XB, no, ABX5H. That okay? AVX5H. Thank you.
Camera is just this place I can see. You can't see my page. Something must have been moved. This better. This better. So, and I take care. Okay, good. Good morning, everybody. I will continue this morning with discussions on the type of motion that is being described as repetitive, and the simplest, which is the simple harmonic motion. And we're talking of a repetitive or oscillatory type of motion whereby an object moves back and forth in a repetitive manner. And we used the spring as an example whereby if the spring is subjected to an extension, there appears a restoring force which returns the spring to equilibrium position. Now, for this type of motion, there's an echo. The time measured for a complete oscillation whereby we have extension restored by appearance of a force, the spring force moves it back to its initial configuration, back and forth, is defined as the period which the equation on the screen describes. That periodic time is equivalent to the formula that 2 times pi multiplied by the square root of m over k. M here is the mass of the object, and k is the spring constant. And the mass, the SI unit for mass is kilogram, and the unit for spring constant is Newton per meter. That's definition on your screen. We will have course to apply it as time goes on. Now, consequent to an oscillatory motion occurring whereby there is a traverse of the object moving back and forth, the period as defined in the previous slide is linked to frequency given by the boxed expression. For this type of simple harmonic motion, the frequency is equal to the inverse
of the periodic time. F for frequency, T for periodic time. So this is the definition that relates the frequency to the periodic time for the simple harmonic motion. And I can go on now using the expression in the previous slide, which is this, that the periodic time is equal to 2 times pi multiplied by the square root of m over k. If I use this expression, I substitute it for the periodic time, I can express frequency of the periodic motion of a mass attached to a spring. That comes out to the bottom expression as the frequency is equal to 1 over 2 pi multiplied by the square root of k over m. It's very intuitive that if you have frequency, you can relate it to the periodic time. And the units for frequency are given either in cycles per second, that is number of oscillations, complete oscillations in 1 second, or given a common name called hertz for describing frequency. And a third relationship for oscillatory motion of the simple harmonic type, we can link the frequency to another important parameter describing simple harmonic motion, angular frequency. The angular frequency given by letter omega, small letter omega, is equivalent to 2 times pi. Remember, pi is approximately 3.14 radians. So 2 times pi times the frequency. If I input the relationship for frequency in the previous slide, I use it to knock off the frequency in this boxed expression. Then I can write frequency, angular frequency in this case, as equal to the square root of spring constant over the mass. That is the quantity called angular frequency. And the SI unit is given in radians per second for angular frequency. Actually, if you look at the boxed expression, I can replace frequency here, as you can see on the screen. My cursor is pointing at that parameter, the frequency. I can use the inverse relationship. I can use that inverse relationship and replace it with the periodic time, since frequency is just the inverse of the periodic time. And I can write the angular frequency, I can write it out as equal to 2 pi divided by the periodic time as angular frequency. Now, easily, we are looking for parameters that are used to describe a repetitive or simple harmonic motion. So again, the parameters are the period, which is the time to make a complete oscillation, Frequency is the inverse of the period and angular frequency, which is given by the expression shown on the slide. We are now going to apply these concepts and take an example to walk through so that you see how this fits into description of the type of motion described as simple harmonic motion. I'll take a moment out now, and for attendance purpose, I will give you the code which you key in to ascertain your presence. The code, the first code for today, D, capital letter, D8, S, capital letter, 3, 6. Again, D8, S, new. Let's solve the problem. We have a car, 1.3 times 10 to the order of 3 kilograms. That's the mass of this car that is supported by 4 springs. So I can imagine that the car is like a board. And the mass car, the mass is resting on the springs, and these 4 springs are the same, having the same time constant, spring constant. And the value for the spring constant, 2.0 times 10 to the order of 4 Newton per meter. So again, we have a car simplified by just looking at it as a box. Excuse me. The camera is off. Slide. Mass 1.3 times 10 to the order of 3. That is the springs, 4 springs. Normally cars are resting on tires, but for us to be able to look at this simple illustrative problem, we assume that the car is resting on 4 springs, and the springs are the same with a spring constant of 2.0 times 10 to the order of 4 Newton per meters. Now, in this scenario, we have 2 people resting inside the car, and their combined mass is given as 1.6 times 10 to the order of 2 kilogram. So the problem now in this example is we are to determine the frequency of vibration of the car if it goes over a pothole. You know your experience, you're in a car and then you hit a bump. There is a kind of a sudden lifting. And in this particular case, since the car is on springs, so there's going to be vibrations considerably. So we are to find the frequency of vibration when it goes over a pothole. And after having determined the frequency, we are to find the period corresponding to that frequency, and lastly, the angular frequency. This is idealized scenario, but we just want to use it to test the principles, the way this problem can meaningfully apply to the concepts we are dealing with. To make life easy and something that we can justify at the end of the day, we are given an assumption that the weight is evenly distributed. So I will give you a minute to just run through and take this in as a problem that describes oscillation. In this case, we have springs bouncing, and we are to determine the frequency of that vibration and the period, and lastly, the angular frequency. So that's the problem we're looking at. Yeah. Okay. All right. So let's assume now that we have taken our time to look at this problem carefully. One good thing about physics problem solving is that when the question is well posed, at the back of your mind, you should know the principle, the guiding equations you will need. And once you are clear in your mind, you also look at the statement of the problem and check out the given parameters. So once the parameters are picked from the question, you make substitution into the relevant expression and you work it out. So we run through this. The solution here is that we need to have the mass, the total mass of the system, which is the mass of the car and the mass of the passengers all together, because this is the total mass resting on the spring. And remember, we are making an assumption that the mass is uniformly distributed. So if that assumption, that's why I highlighted in red, so that you can see that that simplifies issues about unevenness and balancing and all that. So in essence, if we make this assumption, which I highlighted in red, the mass on each spring, there are 4 springs, and the mass is evenly, uniformly distributed. It will be on each spring, we can roughly assume that it will be a quarter of the total mass. And if that holds, I can now work it out, assuming that the total mass I'm representing as letter M here is the equal to a quarter of the total mass, which is the mass of the car and the mass of the 2 passengers. So if you add all these together, as shown in the worked numbers there, you add them together, you come up with a number as the total mass, 365 kilogram for the system. That is total mass. Now, since we are out to determine the frequency, that's the first one, I will, for a moment, just flip back about 3 or 4 slides to show you the expression that you will apply. Now, the bottom expression here tells you that if you want to calculate the frequency for a periodic motion, simple harmonic type, is going to be 1/2 pi multiplied by the square root of the spring constant divided by the total mass. So this expression is what we will have recourse to use. So I'm using this expression now. I'm coming back. So having determined the total mass, and we have been given the spring constant. So each spring will work it out that the frequency for uniform distribution of the mass, it will be equal to that expression, which is F equal to 1/2 pi multiplied by the square root K spring constant divided by the mass. So if I now plot in the relevant numbers for the spring constant, for the total mass, a quarter of the total mass actually, because each spring is taking a quarter of the total mass. So if you work it out, you come up with this number as the frequency, and the unit is given in hertz, 1.18 hertz as the unit. And I can tell you that this same number I can express, instead of using hertz, I can write it as cycles per second. It's the same thing. That is the first part of this example. Now, having obtained the frequency, we're to determine the period, and very quite easy after this that once we have a frequency for simple harmonic motion, the period is the inverse of the value of frequency. So I put it in this next slide. I put the number we've just determined as frequency. So the period is 1/, the frequency. And if we work it out, you come up with a number for this same example as 0.847 seconds. That is the period. And the last part, which is to determine the angular frequency, again, you must know these expressions routinely you will need to apply. So the expression we have used before, I'm going to invoke here, that the angular frequency is equal to 2 times pi times the frequency. And having obtained frequency in the previous slide as 1.18 hertz, I can now put that into this expression on the right-hand side and work it out, and I will come up with 7.41 radians per second as the angular frequency. I believe I'm clear with this example. A smart student will get hold of a textbook and do some practice working on more examples so as to give you more grasp on how to handle simple harmonic motion. Now, up till now, I've been discussing simple harmonic motion relating to motion on a spring. We have a spring that is extended. In the last couple of lectures, you will have seen the slides. We have shown a spring that experiences this type of simple harmonic motion, is extended, compressed, extended, compressed, and each stage there appears a restoring force that is governing this type of motion. Now, let's just open our minds up a bit. Suppose we have a mass. Look at the slide carefully. We have a slide placed at a point P, and it moves. You can see the arrow. The mass moves along a circular path. It prescribes a circular path, and a complete cycle goes starting from a position, traces out the circular path, and turns round, and eventually comes back to the same point. So it's repetitive. And this type of oscillatory motion is also governed by the same consideration we have talked about up to now as a simple harmonic motion. And one particular thing about this type of motion is that though it's circular, it describes a constant radius path and goes round and comes back to the same point. Now, at any point along its path, we can project to the x-axis an equivalent distance from the origin, so that if you say you start from where the cursor is here, the original value of x is equivalent to a, and then as it moves round along this circular path, the value of x, the displacement, changes, and it goes round, and each position is described. We know that the radius is constant, but what changes continuously is the angular displacement. See this on the diagram represented by letter theta. That's the angular displacement. So when it starts from along the x-axis, the angle is 0, and as it moves along the circular path, theta increases, and it gets to the y-axis here, theta becomes 90 degrees. Going further, theta increases to about 180 degrees. And then it returns. So the projection of the distance along the circular path makes a complete oscillation a circular path goes and comes back, and then it returns and repeats. So it's oscillatory motion, starts from a point, makes a complete turn and comes back, and on like that. So this type of circular motion is what we are going to relate using the same consideration as we have used for spring when we're looking at the motion, and it's the same oscillatory, but we are looking at projection now of a mass moving along a circular path, making an angle theta as shown on the screen. I will also pause now and give a code, a second code to mark attendance. Before we go further, I will dictate the code. The letters are in capital, and the code, the second code, LBX4Z. LBX4Z. I'll show this on the screen. LBX4Z as the code, second code for attendance. Again, my mistake. Now, this oscillatory motion we are looking at, we want to seek and obtain an expression that gives the position of this object represented on this slide that is moving with simple harmonic motion as a function of time. Now, we have this mass moving around and describing at each point along the path angle theta it makes with x. So as seen on the slide, the projection of this object on point P on x-axis is given as our displacement. So that displacement is obtained. X here is adjacent to angle theta, and the distance from the origin that prescribes the circular path is the length A. So cosine of angle theta is the adjacent, which is the distance we seek from the origin, divided by the adjacent. Cosine theta is equal to displacement x divided by the amplitude A. So if you rearrange this expression, I can write the displacement now as equal to the amplitude A multiplied by the cosine of angle theta. So this expression you can see from trigonometric identities here. You can see that x is equal to A multiplied by the cosine of angle theta. Now, assuming now that the angular speed is constant, as indicated by this arrow, then we can write out that theta, linear speed is distance over time. Distance over time, speed. But angular speed is angular displacement, in this case, theta divided by time, t. So, in essence, we can replace theta in the expression here by writing it as the angular speed multiplied by the time. So, x is equal to amplitude A multiplied by the cosine of angular speed and time. So this bottom expression indicates for this ball that is rotating at a constant angular speed as a projection on the x-axis that is equivalent to the amplitude multiplied by the cosine of the angular speed multiplied by the time. So having had this now, we want to demonstrate and explain how this relates to other parameters for the motion. In this case, the simple harmonic motion we're considering. Now, for the displacement, because it is angular displacement, it follows a path. If you look at this red curve, what obtains is that if it starts from the point O, capital letter O, from maximum displacement, the displacement reduces. I will explain, but just for you to get it better, look carefully at my diagram. This curve, the red line is indicative that if you look at the displacement, which is the vertical axis here, against the horizontal axis, which is the time for the motion. And the expression we had in the previous slide gives displacement as a function of the angular displacement, linear displacement as a function of angular displacement. So what happens is that the path traces a curve. The curve is repetitive. Look at this red line. And if you start from the origin where let me go back a bit. If you look, we are starting from here when the displacement is equivalent to the amplitude A. So as the mass moves along this circular path, the displacement changes according to the expression A multiplied by the cosine of omega t, sorry. Then the interpretation is that if you now plot displacement as a function of the time elapsed, we have a curve traced out as shown on this diagram as a function of time. And periodically, a time that corresponds to the periodic time is when the particle returns. It goes from a start time here and traces out the distance changes and goes far, and then as the time elapses, it comes and it returns finally to its starting point at exactly a time period corresponding to the periodic time. And when that occurs, if you look at the curve carefully, the point it starts here is exactly the crest. It starts from a crest and it ends up again at a crest. And the distance is corresponding to one periodic time. And halfway, that is half of the periodic time, is when the object goes opposite along the circular path. You remember, we are working on this relationship. Displacement is equal to the amplitude multiplied by the cosine of omega t. And you recognize that omega is equal to 2 pi divided by the period. So when you chunk this expression into this equation, it will tell you the corresponding displacements at stipulated positions. So this is what happens for displacement, angular rotation, and it's repetitive. It comes back. Now, if you go a bit further and look at other parameters, then we apply the relationship that from displacement, we can determine the velocity as the derivative, time derivative of the expression, this box, this expression at the top for displacement. So the velocity is equal to the time derivative of the expression for displacement. So if you take the time derivative of this expression above, this comes out as omega A multiplied by sine. The cosine, when you differentiate, changes to a sine function. I'm sorry, I want you to please commit your time and convince yourself that this identity is derived from the displacement. So if you differentiate displacement with respect to time, we get expression for velocity, which in this case is minus omega A multiplied by sine. So when you differentiate a cosine function, you get a sine function. And further, we can determine the acceleration. And the acceleration is also consequent on finding a time derivative of the velocity function. So we differentiate the expression here, minus omega A sine omega t. We differentiate it with respect to time. And if you do that differentiation, you get minus omega squared A, that's the amplitude. The sine now will change to a cosine function, and then you have as expression for acceleration. So 1, 2, 3. These three expressions are interrelated, describing the motion we're looking at. And in that case, I will draw the complete diagrams, which shows the topmost panel shows displacement as a function of time. The middle shows velocity as a function of time. And lastly, the bottom shows the acceleration as a function of time. And the expression is governed by the relationship where x is equal to a the amplitude multiplied by the cosine omega t, the velocity is equal to minus omega a multiplied by sine omega t. And lastly, the acceleration is minus omega squared multiplied by the amplitude times the cosine. Now, what you see here is that for the displacement, it follows a cosine relationship of the angular displacement, whereas velocity follows sine and acceleration is cosine. And there is a shift at the origin, which is this line, when x at the origin, the x is maximum for displacement. At the start, at the initial start, the velocity is 0 and acceleration is maximum. So this is the conditions guiding this type of oscillatory motion. I will take a pause again and give you the third code at this time for marking attendance. And attendance, the third code for attendance is all capitals, all capital letters, S, P, Q, P, S. Again, S, P, Q, P, S. On the screen, you can see letter S, P, Q, P, S, all capitals for the attendance. In the dying moments of this presentation, I want to make you to understand that when we say we have a simple harmonic motion and that the oscillation occurs from maximum amplitude, goes through a middle position when the displacement is 0 and swings back to the other extreme. So we have a swinging back and forth between one extreme to the other extreme, and it can continue like that. That is an ideal system. It's not true in real life. So in an ideal system, when we say simple harmonic motion, we assume that the swinging back and forth is maintained indefinitely because of the restoring force. But in nature, it's not so true. In real system, there are frictional forces present that retard the motion. If you have a swinging, somebody's on a swing, and you start, after a while, because of air friction and some mechanical frictional forces present, its rest gradually dies down, and such situation is called damping. So when we look at oscillations in real life, there is some frictional forces present that produce reduction or retarding of the motion so that the oscillation cannot continue indefinitely. So the essence of the friction is to reduce the mechanical energy of the system as time passes, and such a motion is said to be damped. So damped oscillation. If you now look, the one I showed before, when there is no damping, we have oscillation for displacement going smoothly and maintaining the same amplitude at subsequent time periods when there is no damping present. But what I've just explained and introduced is that this is idealistic. It's not real life. In real life, what happens is that if you start from an initial amplitude, it swings. After a while, it makes a complete oscillation. By the time it makes a complete oscillation, the amplitude will have reduced. So subsequent oscillations swinging back and forth, the amplitude reduces until eventually it will come to a stop. And that is called damped harmonic oscillation. And I think at this time, I will stop for today. Thank you very much.
Hello? Hello? How are you, sir? So, Ope o.
Can you hear me?
I can hear you loud and clear.
Please use your camera. I want to see your face.
Okay, ẹ jẹ́ kí n gbé ti fóònù kúrò kí n bàbá kọ́ sí tavirus. Àwọn tí wò pé kí ló ń ṣẹlẹ̀? How you can see?
Yes, you can see your face now. So you're welcome.
Yeah,
I think
okay, sir.
we can start the exam because of our time. And let's start by the introduction. I will start from my extreme left here. So because of that, we start the introduction. Introduce yourself.
Thank you, sir. Dr. Osanda, chemical engineer.
You're welcome.
Soil science and land resources management, faculty of agriculture. Professional and as the official.
Okay. Can you introduce yourself, sir? Okay, you have unmute yourself.
Yeah, muted, sir.
Unmute
Okay.
yourself.
All right. It's all right, sir. Okay, sir. Can you hear me now, sir?
Yes, we can hear you.
Professor Adekunle, Department of Chemistry. Although by extension, drinking hot tea here in South Africa.
I wear cap today. Chief examiner, supervisor. And there is a misunderstanding on the thesis. This is a qualifying exam. It's not an oral exam. So we are about to candidates. Final. So this one will lead us to fill from A. So we want this panel to please dissect this work very well, so that at the end of the day, the quality that will come out of this work will be a very good one. So out of this, at this point now, we'll bring the candidate in. So the candidate, you have 20 minutes on your presentation for the item. Okay.
Hello, sir. I can't hear anything again. No.
No,
Okay.
we have some technical issue here.
It's all right, sir. It's all right, sir.
It's been attended to.
All right, sir. Sir.
Sorry, Professor Adekunle.
It's using this each week. Well, trying to use it go in.
Are we set?
Yes, sir.
Okay, you have 20 minutes for the presentation. Start counting now.
Thank you, sir. Thank you, sir. Thank you. My name is Aditya.
Who is Adekule?
My name is
Who is Adekule? Who is Adekule?
I'm here with you, sir. I'm here with you.
Okay, so
Thank
we're
you, sir.
about to start.
Yes, sir. Yeah.
Okay.
See the slide. Yes, sir.
here for my qualifying examination of television of CBT, phosphate of laser plate concentrates. Here is the site of the phosphate of identity. Background information. Global phosphate of production in 2019 was reported to 47 million. According to Neptune 2019, which Sokoto Basin has 5 to 10 million, according to Akere and Western 2006. Sokoto, there are 2 major basins for phosphates, or each is the Sokoto and the Delta Basin. According to the survey of 2010, worked on their own basin, which entails also some LBT and other of them, in which it also saw an LBT, predominantly granular phosphates, but the other phosphate type like nodular and phosphate. Then Superson et al. Worked on the characterization of this phosphate ore and was able to determine that the hardness is 5 on more scale and gravity is very good gravity of 2.65 and combination work index of 16.97. A lot of work has been done on the phosphate ore, among them work done by Superson, and each was majorly on characterization of the phosphate ore. Excel and et al. 2021 also worked on this timing of phosphate and combined with cross rotation method, in which you are able to achieve a grade of 21 weeks percent and a recovery of 80%. Other material work as presented. Research gap. Nigerian researchers carried out characterization of phosphate ore from Sokoto, and the parameters for the physical and chemical concentrates of this local phosphate ore are yet to be determined. So this work will determine the parameters to enable the reduction in the impurities of this local deposit in LBT, and also serve as substitution to imported fertilizer and inputs like phosphates. Statement of government. Phosphate rock are the main source for elemental phosphorus used in the production of fertilizer. Nigeria has a large untapped phosphate deposit in the Sokoto and the Okun, which is the Ogun Basin. However, these phosphate ores, they are of low grade. It has high oxides of calcium, magnesium, iron, and aluminum, which need to be reduced via beneficial mix. So they are an accepted grade of above 20%. The application will combine environmental, method, physical, and chemical session, as this study. Aim and objectives of this study. The aim of the study is to upgrade the locally available phosphate oil deposits in PBT to fertilizer grade percentages. And the objectives are as follows. One, to characterize the as received PBT phosphate oil. Two, to determine the optimal calcination parameter for this, and to identify the most effective, the better effective gravity separation technique between digging and shaping table, to determine the best oven and agitation leaching condition. 5, to determine the kinetics of the oven leaching mechanism. And then lastly, to determine the crop rotation parameters to obtain the better grade of fertilizer. Justification of research. Research gap. Justification of this research is the research gap that the parameter for physical and chemical processing of phosphates are not available in literature, and this research will produce it. The economic factor developed processing flow charts for this will be available for fertilizer industry. The scope of this research is limited to the development of a multi-beneficiation routes for local phosphates sourced in PBT states via gravity separation technique, calcination, leaching, and fortification. Expected contribution to knowledge, the study will produce a mineral processing flow chart, which will comprise of combination of calcination, shaping table, digging, leaching, and fortification for effective beneficiation of PBT phosphate oil. The list of items and their availability to be used for this research are shown. The list of equipment and the availability is as presented. The flow chart for the study is shown, in which the received phosphate oil will be milked down to lower size lab Pascal mini machine. Then the size will be further reduced using ball wheel. Then the oil will be passed to 3.5 micron size of a sieve, and digging and shaking table will be used as the piece of production base for the PBT oil and calcination and leaching. As shown are the phosphate oil of different particle size in the first picture, and the Morphle furnace and other methods used. The calcination process, the experimental design is that particles were filled using -75 to -125 to 75, -250 to 125, and different temperature of 800, 850, and 900 degrees Celsius respectively. The methods were for the shape paving, but was used favoring to 3 factors, which are the pulp density of 50 and 25, and 10 and 40 minutes, then high and low flow rates of 5 and 15 liter per minute respectively. The factorial design for the hydrochloric acid leaching process is as presented at a different level of 3 by 2 factorial. The design for the calcine sample is as shown using 3 parameters of concentrate, temperature, and time. Preliminary results. The as received phosphate oil contain using SCM. The micrograph is as shown in figure 2. Then the elemental composition derived from EDS shows that the phosphorus in the depot is 12.21, which is the low one, and a CA of 26.09. Then we have know that both the phosphorus and the calcium are in their oxide form of the ore, respectively. That's why the oxygen weight percent is 61.7. The binary result for the assistive using SRF is as shown, in which there are 22.208 of the composition. The phosphorus pentoxide in composition is 20.208. Then the slime of the assistive ore has a high silicon of 17.67, and which is, and the slime is the after desliming the ore, the slime collected at the from the process was visualized using SEM, which is presented in figure 2, and the EDS is shown. Experiment was done to consider the effect of grinding time on the mass pass of the 355 micron, which shows that at 12 minutes, that's 86.08 weight percent pass in the 355 micron size of a sieve, which shows that at this time, it is the optimal time to stop the grinding process. Any other time above this period is marginal time. Same result, the same process was used varying the grind time at 10 minutes interval, in which at 40 minutes, 87.01 weight percent of the ore passed the 355 micron size, as shown in the graph. The pulp density was also done to determine the flowability of the ore when mixed with water, in which this result shows that there is an inverse relationship between the pulp density and the mass of water added to the ore, in which at 83 grams of water, there is going to be 0.33, which shows that 30% of the solid is in the pulp. As much water is added, close to 5% of the phosphate ore is in the pulp. So then the calcination process done for the process shows that there is a great loss in the assistive phosphate ore when calcined at 900 degrees Celsius for less than 75 micron size of phosphate ore. The C series shows that at 900 degrees Celsius, the assistive phosphate ore suffered a lot of loss of weight, which is loss of ignition at 900 degrees C, which the optimal value is achieved at C. So the SRF results of calcined elemental composition of the samples were also done, and are shown in this C1, which has less than 75 micron particle size, has the optimal value of 24.326. The result was further confirmed using TDA to study the loss of ignition against temperature, in which is the micrograph shows that there is a sudden weight loss at 300 degrees C to 600, which shows that a lot of organic matter in the phosphate ore was lost due to temperature. Then there is a steady response to increase in temperature from above 600 to 852. SRD results on the calcined sample shows that the ore is predominantly an hydroxyapatite sample of 87 weight percent, whereby there is sparse, which shows presence of silicon of 10 weight%. The result is as summarized here, it shows that 75 micron as the optimal value. Then the SRM results done on Jigme shows that the first run, which is the concentrate, has the highest phosphorus pentoxide of 23.597. Likewise, other tildecanes, which has the lowest. Checking table result also reveal that P2O5 have an optimal value when the condition is a low bulk density of 15 gram per cm cube and high flow rates with high grinding time of 40 minutes. Which shows that the better gravity separation technique is shaking table to Jigme process. The shaking table shows a better result to Jigme. Elemental conversion was also conducted on niche sample using different bases and acids like NaOH, Na2O3, HNO3, nitric acid, HP, phosphoric acid, sulfuric acid, HCl, and nitric acid is as shown, in which phosphoric acid has the optimal value of 24.61 grade and recovery rate of 98.18. But the calcium oxide of this sample is 52.44, which is not that good enough, in which HCl was considered of a better grade of 48.51 weight% and a grade of 22.82 when opened in an open condition. Experiments conducted to study the effect of leaching on calcined sample shows that a sample C1 has the optimal value, which is of low concentration, high temperature, and low leaching time to other samples of its kind, which is C2, C3, which has a higher concentration of 1 m, 1 molar, 1.5 molar, in which show that at higher molar, the phosphate all suffered a lot of leaching. A lot of its values have been leached off the phosphates. Yet analysis also shows that in which A means that at higher concentration, B means that A means that higher concentration, lower temperature, lower time. B means lower concentration, higher temperature, lower time. So likewise, all these variables are considered, in which BC has the highest negative value of minus 0.00010, which shows a high effect on the leaching process. At this BC, it is of low concentration and high temperature, high leaching time, which shows that it has a high effect on the leaching process, which was buttressed with the calcination, the leaching of calcined sample of the deposits, which is shown as E. The BC is the same condition with the E sample that has the least grade of this presented as 10.69 and a recovery rate of 19.16. Elemental composition to study the double leaching process, in which the sample was first leached in 0.5 molar of HCl, was further leached in water, and another one was first leached in 1.5 molar of HCl, then leached in water, which shows that as the sample was leached in water, it has a composition of 23.209, Then when it was further reaching 1.5 molar of ACl, there's a drop in the grade to 18.38. Then when the sample was first reached in 1.5 molar of ACl, there's a sudden drop in the grade to 14.872. Then when it was further reached in water, there's an upgrade of 20.678. Which shows that the higher the concentration of this acid affects the grade of the ore. So which was confirmed by Tagavi et al. 2020, which document that as there is a decrease in phosphate content of ore from 27.74 grade to 25.33 weight%, when there is increase in the dosage of the acid added to the niche sample. As shown is the effect of agitation on the leaching. It was combined using a magnetic stirring, which has an oxidate, which has an 18 and the agitation was done at high agitation, moderate agitation, and low agitation of 200 RPM, 300 RPM, and 500 RPM respectively. The sample recorded are A1, which 1 represents the high agitation, 2 represents the moderate agitation, 3 represents the lower agitation. It shows that at higher agitation, the sample suffered a greater loss, as shown in the table. The chemical composition of the optimal condition achieved in shaking table was also combined with the leaching process and was studied against agitation, in which the result shows that as the agitation has negative effect on the shaking table samples from 24.872, which is the starting grade value, to the least agitated sample to 20.934. Using the calcine sample, it shows it appreciates from 21.394 to 24.819, which shows that agitation helps improve the grade of calcine sample. But when it comes to degree, it's in between the performance of the shaking table and then the calcination sample, in which there's an improvement in from 20.88 weight% to 24.235% at moderate agitation of 300 revolution per minute. The graphical representation shows the rate, recovery rate, and CaO to P2O5 of the jiggling, shaking table and calcination respectively, in which calcination shows the best performance from the 3 methods. Conclusions: the first objective of this research was achieved, in which the achieved epithelial phosphate oil and is characterized. The second objective of this result also revealed that the optimal calcination condition for epithelial phosphate oil is minus 75 microns and a temperature of 900 degrees C at a holding time of 1 hour. The third objective also shows that shaking table show a better performance to jiggling process. Then the fourth objective has been accomplished, in which it has been established that leaching should be done at 0.5 molar of ACl at 90 degrees C for 90 minutes. The fifth objective is still under process, in which the fourth rotation will be carried out at footer for further revision of the references. Thank you for your time.
Well, you are about 3 minutes behind the schedule. So we'll take note of that.
Thank you.
So the candidates before us.
I think can we allow them to sit down?
Yes, take your thesis. And then you correct your issues.
Take your thesis with you. So that
Definitely.
when we are correcting,
You stay there, but the way it's happening.
Okay.
I will advise you that we collect all our statistics, you implement the potential as stated on it. That's really my own first observation of presentation. You don't remember your slide.
So we couldn't follow.
We are just reading the whole. So we don't know which slide we're talking about. So even if we want to correct now, I mean, we don't know which slide.
Which one do we refer to?
So please take note next time, but this is just qualified. When you are doing your work, and make sure you number. So that one will make your work easier for you. You're able to say, now go back to slide so. So they'll be able to. That is about the slide. Then two, we should also table. And for me, I don't know the meaning. BC, what is BC before Christ? So I don't know the meaning. So maybe Professor Adekule from South Africa. There is a money in South Africa, they call BC, so he can tell us. We see
Yes.
yes.
Most of the symbols,
So
even if it's
then the title of the table, there is something wrong with it. I put it here, check your PG format. Check on the PG format. Please. That's that would be the first problem that you have with the external example. So please check your thesis. Then another thing, you have something.
You can see that I'm taking note of it.
Oh, you can read of the
Anyway, I'm not here with chemicals. Don't be scared.
He's hearing us.
Please.
So,
I'm with you, sir.
any observation from your presentation? That's my own comment.
like
Okay.
the presentation to me look better than what is now.
Than the thesis.
Probably because I was able to explain what C or B stand for. So, it seems like
Concerning the presentation, I would like to take him up on some general things he mentioned. The beneficiation method you used, apart from, okay, you've not done flotation.
Yes.
You mentioned, apart from shaking table, which other one did you use? In your presentation, you've been mentioning jiggling. Maybe you are doing jiggle. Now, I don't know whether pay attention to this question. What's the basic science behind force flotation, shaking table, and jigging? The basic science behind it.
Gravity. Difference in gravity of linear and modules.
Density, and one more thing, size also matters.
Yes.
Now, in your presentation, you mentioned for some sizes you mentioned minus, for some you mentioned plus. Let me pretend for a few seconds that I don't know what those things mean. If you show me a particle size, let's say minus 75 microns, does it mean it has negative particle size?
What it implies that it passed through the sieve. That's the connection.
Let me pretend I still don't understand what you are saying.
Yes.
break it down so that we'll all be on the same page.
Okay, what it implies that when sieve are stacked,
Okay, let me give you mention one standard sieve.
one standard sieve, 125 micron.
Let's say 125 micron. The one which is retained on the sieve is labeled what? The one which passes through is labeled what?
Okay.
With respect to the sieve size.
The according to the sieve size, the one that the subsequent sieve that is above the one.
Be careful before you put your laptop down.
The one that is above the 125 micron, maybe there is 250 micron, above it. The one
asking
the
fraction
Okay.
on the sieve is called what?
I give you just one sieve
Okay, the fraction that is above
that is retained on the sieve.
125. It was 125 micron. The one that passes is minus 125.
Yes. Meaning that minus means smaller than
Yes.
that size. Plus means above that size. So that won't be confusing people. And you said in your objectives that you will be doing kinetics.
Yes.
Can you explain what kinetics is? So that you won't do what you cannot explain.
The kinetics is the study of how the surface area of the ore affects the leaching process of the ore. For instance,
Reload. Now, okay. Ever heard of shrinking core model before? But you did acid leaching.
Yes.
Okay. Now, you did chemistry as an undergraduate.
Yes.
Now, from reaction kinetics, what do you think kinetics mean?
Oh, the study of entropy and
no. Don't end up adding what you cannot explain to your objectives. But this one has to be there because you've done part of it. Now, if you are looking at kinetics, you are looking at how what you are dealing with, how the modification is taking place with respect to time. For example, you are using acid and you are checking probably the size with time. You end up plotting something against time. What are you studying? You are studying kinetics. Once it stops changing, you are steady state. You stop. But as long as it is changing with time, what you are studying there is kinetics. Well, before I stop with what I'm asking here, I'm only picking you up based on what you said during your presentation. You mentioned the word pulp density. What's the difference between true density, bulk density, and pulp density? True density, bulk density, and pulp density. Write them down.
If you know them down, just say I don't know. Then you will write it down. Check it.
Go and check it. True density, bulk density, pulp density. Please do. You know the degree you're about to get. Is it an engineering degree or a philosophy degree? I thought you said engineering. So you'll be able to raise it like one. Well, let me stop here for now. Although you still hear more of my voice.
Okay. Yes.
Okay, Professor
Yes, sir. Yes, sir, boss. Yeah, the presentation is fair. And I think the major thing that struck my mind when he was presenting is about the allusion that people have not characterized this material before from that region in particular. I stand to be corrected. How much of literature search have you done to come into that conclusion? Because it is apparently not, to me, correct that people have not done some of these things you are trying to look at all. How sure are you?
No, prioritization has been done on most of the deposits, Sokoto, Ogun Basin, and the rest. So like Professor
Should be a song.
has worked on FPT and on also phosphate depot, in which she worked on, she compared the nodular and the vascular phosphate to determine the grade of the votes. And likewise, other Sokoto deposits have been done regarding the deposits in Nigeria.
So that statement is very, very wrong, please. You make it like a natural king. You are trying to condemn the effort of what other people have done before. Anyways, as we continue, maybe I'll ask more questions. On the thesis, I don't know, maybe when they get there, I can make my comments. You know, but the procedure is fair.
You can go ahead, sir. Go ahead, sir.
Okay, if that is the case, I think for me, from my scan through the thesis in terms of formatting, compared with other things I've read, about in the last two months, I've read close to 5, you know, from different universities. Its formatting is fair. In terms of the table of contents corresponding with what we have in the body of the work. It's similar to figures and the others to plates. I only can pick up 1 or 2 errors in that. I was wondering that, okay, that would be very nice that our students who are waking up to the use of using computer tools to fix some of these things. So kudos there. However, I want to quickly point out some little mistakes that you make. What is the difference between microscope and microscopy?
Microscope is a device to check microstructure. Why the microscopic is size.
You go to your serial number on table 3.2, page 58.
Okay. List of movement and use.
Yes. That one comes before that one. Electrical, what should it be?
Scanning electron microscope.
Microscopy.
Right.
You said correct it as scanning electron microscope, not microscopy.
Not there, sir.
Microscopy is the, let's say, the techniques. Microscope is that instrument you are using there.
Not there.
To be able to know the difference. Electrical weighing balance, not electrical weight balance. Are you with me?
Not there, sir. Yes, sir.
And in the previous table 3.1 too, and also on your experimental, whenever you find me, the L there should be capital L. You must correct that on the table 3.1 and under your experimental.
Right. Okay. Not there, sir.
On that same table, this X-ray fluorescent what?
Theorem
Yes.
number 5. Theorem number 5.
Okay.
X-ray fluorescence, what?
SRM.
F, what is that F?
Fluorescence.
It should end it at, because you are using the equipment now for your measurement, X-ray fluorescence spectrometer.
Spectrometer.
Some use it as spectrophotometer, but still it's the same. And the same thing goes with the X-ray diffraction spectrometer. Okay, the table 4.11, page 140.
Page 140.
Best of all. Okay, best of all. I don't know what we need or
not, yes, and not one. It's not 141. You have to page 140. Are you with me?
Yes, sir.
Tape 4.202. That, yeah, it should be table 4.20, not 4.21. That's under table of content. Anyway, after the table 4.19, it should be table 4.20. I was looking for table 4.21 in the test. I didn't see, and I came back on that table of content, and I discovered that you jumped 4.20. Are you with me, sir?
No, sir.
You didn't get it?
Yes, sir.
On the page, Roman figure S, page 10.
Okay.
Go back.
Yes.
Don't go to the...
Yes, this on Philips. Okay,
Did you get
there's
it now?
4.20.
Okay. So I was looking for 4.21 in the body of the I couldn't find. I went back there. It's that you jump after 4.1. Plate 4.1, page 93. Page 93, that plate. Can you figure out something there that was wrong?
Page 93.
93. Yeah. As you see, okay, Ivy.
Okay. Your page 4. Your page 4, section 1.2. Sorry that I'm taking you back. I was just looking at and there. Page 4, section 1.2. The application of a combination of section 1.2. That's your justification.
4.2.
Section 1.2. The applications of a combination of pyrometallurgical, physical, and chemical mineral processing have been used to reduce the impurities. Hence, this study has something is wrong there.
Exactly.
You already had you have solved that means they have solved the problem. What are you talking about this study again?
Will be used.
Listen to his question.
Okay.
From all what you've written here, point out what the problem you are solving is.
The gap.
Which gap are you trying to address?
The gap is to upgrade the low grade onto a fertilizer concentrate.
Something which nobody has done before, that you are contributing to knowledge.
For the applicable limits.
Go and look at it again.
Yes.
That's what Prof is asking you.
Yeah.
That last statement doesn't show problem at all.
At all. At all. It's contradicting. It's like they have already even solved the problem. So I don't know which study are you talking talking about again. If all those have
study
been
the
used
solution.
to reduce the impurities and because that's what you are also doing to reduce impurity and make it a commercial grade. And some people have done that. I am still saying ends this study. You have to recast. Okay, I think it's the same page 2. I think section 1.4. I'm not too comfortable with this, your statement. The parameters for the physical and chemical processing of ABT phosphate ore are not available in literature. And this research will produce it. It makes it look, too ordinary, not scientific. Huh? We produce it. How? So you have become a producer. Please try to recast it. And let it sound more scientific. Okay, I'll ask questions more as we move on. More questions. Okay.
Thank you.
Okay, thank you, sir. I have another assignment by 1:30.
Okay.
So please kindly allow me to. My observation on the thesis and methodology. Let me say first that your literature review is a little bit weak. That's why they are asking you difference between density is if you have done it before. You're going to ask you. Have you? Then your year is 1986 to 2024. The literature that you review. 2025. The two of them are missing. 2026. So kindly update them and the results that are missing. Like them. What is WT? White House. Wait. All those things you have to define the applications. All those symbols and abbreviations you have to put micron. Some people somewhere micron is different. To us in engineering, 10 is to power 6. Minus. So you have to define it. You don't know who and who will take your thesis and want to read it. Then you said you analyze with your factorial design. You analyze with Yates and Hodgson. And you can do on Yates analysis. There is no formula for it. And I'm a village boy. I was looking for the formula. I did not see it. Then I saw somewhere at the back. You said minus the upper one, add to the upper one, minus the lower one, which you supposed to have expressed as formula in your methodology. Please take notes. If you don't know the formula, see me after the. There is no free town in Nigeria. Then if you go to your table, all the table, the title of your table, all of them are capital. Is that the PG format? So I put it here. Please follow the PG format. Then the GPS of your sampling point. You just said latitude 6 point something something. Is it north, south, or west? Check. No, check. Maybe I'm not sure.
Nothing.
Nothing
there.
Yes, sir. So check, you will see it there.
That's page 54.
So please check very well. Then your literature, you cited a lot and you did not list most of them. A lot, you will see them there. I took my time as your landlord.
They do justice to the work.
It's official landlord.
Ọ̀gá ilẹ̀ tó lẹ̀sẹ̀ tẹ́ bá tún wá chemistry náà tẹ́ bá wá chemistry tẹ́ bá dé chemistry náà landlord náà lè jẹ́ fún wa ń bẹ̀ So kò sí wàhálà. Ọlájàre pẹ́sà.
He has not paid for match. So maybe you want to bail him out. You just 1,500.
Ah, you.
So we won't because of that scatter anything.
Thank you, sir.
Yes, sir.
You see, you did statistical analysis. Yes, algorithm. If I'm the one, I would have gone a little bit further, analyze with analysis of variance.
Another, yes.
The effect,
Significance.
the effect of all those things, and I did significant.
Yeah, because of parameters, you what we wonder, how do you think there will be that much difference? You can't prove it to me with that. Even when he was reporting the what's it called, furnace to reduce its material under different temperature. The temperature was so close that you want to ask, are you sure you achieve this within those so close range of temperature? But anyway, that's where statistical, calculation comes in.
To apply that, your methodology you put it there. Like do this. Use analysis of variance to establish the effect. So you do that. Then your factorial experiment. There is somewhere you said, I think there's 2 raised to power 3 because you have 3 factors. Then there is another one you have 3 factors. And you still put it as 2 raised to power 3. There is not like that. The one with 3 factors, you have 9 experiments. So it's supposed to be 3 to raise to power 2. That is 3 levels, 2 factors. You need 3, 2. Then your something is 2, 3. Don't argue with your Then so let us check those ones, and I'll try my best to be able to do all the necessary things that it is for you. Thank you. I will hand it over to head of finance.
Thank you, sir. Thank you. Okay. We've been our tenant for quite a long time. As frankly observed by the members of the panel, the thesis is not, the one you're presenting is not defined now. It's not defined. So it's a proposal, not a thesis, a proposal. Everything for your works. And the other thing that I observe is go to the list of tables who are doing the I've seen it.
Yes.
You have to book one. And the case we use is supposed to be essentially proof. Not this particular something that's in use. Then the objective, you have 6 objectives here. PG doesn't take 6.
5 maximum. For PhD, minimum 4, maximum 5.
Maximum 5.
But 4 is usually advised.
Yes. That's why I go to put yourself to. In fact, the work you have done, to me, it's okay. Instead of looking for another objective to, another methodology to support your 5th objective. Now, you develop the kinetics. That landed in trouble today.
He claimed to have done it, but from what I've seen, he has not done it.
So I was thinking that is it possible to compress this your objective into 4 or 5?
And we work on that.
That's the way. Then they have talked, they have talked on the junction of return. It really needs to be fast. Because the parameters of the physical characteristic process of the are not available. How do you say they are not available?
That's to the best of your knowledge.
So, as pointed by Professor, your research is very, very, very good. So, please you have to work on that. Then you are benefiting in the first place for fertilizer grade. What is fertilizer grade?
Above 27.
Up to them. What's the combination of the grade for anything?
Great.
The current grade.
The current grade of the one
The one I'm punching 24.9.
As received.
as received.
22.
As it is 22.
Yes.
But that's both for 0.2.
Yes.
Okay.
And 2 points.
Okay. And you are able to complete 2 words now.
24.9.
24.99. So you are getting closer. Then when you are citing the any reference, don't say from Professor Adesawu, just put Adesawu 2020.
Because the Adesawu you are citing might not be the Professor Adesawu exactly. Might be another Adesawu.
I noticed that all your reports are not.
They are not in eternity.
Right. Almost 90% of it. So please, you have to go.
So there's something with the top.
All
dots. All the dots they are missing.
So please, you have to work on that. Then the way you put your equation, you don't put dots on the equation, then you grab it. Do the equation anymore. Don't do the equation 4. We don't do that. It's with free space. Before you put the equation number. Look at it.
Okay, space and equation number.
Yes. No dots, nothing there. Don't put your
Space.
Then
Flush everything to the right. So that all the numbers are right.
At time you model the equation number with the equation itself. Which is how to take this. Very important. Okay, they have corrected the microscoping, the microscope. Then the way you put magnification, I think you can tie X, not small X. 300 X. Capital. Capital. Then your figures has to be in color. Most because you have the facility to print in colors so that all what you are presenting, we clearly show.
Yeah.
Look at what I'm saying. I noticed in there. Print color. Then some of the what you put as figure to be placed. Like the SEM, no, it should be placed. It should be placed. The place through then those some of the figures and plates are too far from the
mention.
Look at what it will be either the next page if it's not on that page or just a page before or a page after. But I can see some are maybe page 5 after you have mentioned it. So we have the thing that I noted here. They have received, they have seen it. Then the reference is many that are liquid and not cited. Check very well. Check very well. So
label incomplete references.
So for now, those are the things that I noticed.
On the issue of references, on the issue of references, do not to reference URL. URL. Not URL. URL.
Okay.
Websites. How do you reference an internet link? Because after writing everything, the next thing that follows is date access.
Data you are saying that
Because what you see on the internet today might have been modified tomorrow. So put your own date access and please be very careful. Don't end up putting a date access earlier than your PG registration number. I've seen that before. Somebody will CPA 1920 something. Site a date access August 2016. Then you do start this research before you start the program. You get what I'm saying?
Yes.
Lots of people want to cite the date they saw on the page. Which date did you access it? Date of publication is different from date of access for URL. That's okay. And you have noticed some of those things. There are some references that whose names are not written in full. There's one here I wrote a comment there that, did you read the the Russian version? The Russian reference, and was written as you saw it. Do you speak Russian?
Still on that, I noticed that you use a symbol when you want to command something. Authors, we don't allow.
Don't use ampersand and and.
Use and. Don't use symbol.
And there are some that don't have ye. Place tech PG. You are familiar with APA?
Yes.
APA referencing style. Study that. Make sure you get it. Because you are mixing up referencing style. Well, let me stop for now.
Yeah, I'm sorry if I stop. We told you this earlier when you are making the seminar in the department. List of equipment. You have to put the specification there of each of the equipment. On the equipment we have the spec. Like the SCM.
Model number. Although there are some things you shouldn't have listed. The list of equipment only on the graduate list, and there are some figures that are not necessary. Like figure of him putting glassware inside oven. So picture of you picking stones, they are not necessary. But I wonder something. Your sampling style is hand picking. Can you identify phosphate ore visually?
Yes.
Because your sampling site looks like somebody's farm.
That's it.
Can you identify them? Actually?
Yes, and before I visited the site,
you come to my office today to identify some of them.
Because if your sampling method is hand picking, it means once you see a particular ore, you can identify. But the thing is, that phosphate, you can identify them. Can you identify the other ore that way?
I'm familiar with it.
Because I'm wondering how you're able to do that. You know, when it comes to identifying gold, there's something called fool's gold. Ever heard of fool's gold before? But you're a material scientist. Pirates will fool you if you are not careful. Iron pirates. So mind what you write.
You know, when you get to the size, what can you excavate? But at least most of it they are in pillars, you know, and they have different so just people and the deposit. They are scattered almost everywhere.
Because what I'm looking at, if somebody didn't show him that this is what you are looking out for, because you might just find a way to be silent or hand picking.
It's okay. It's not. It's not
Thank you, sir.
okay. We can start taking.
Yes.
You have that.
So we're doing that.
Yes, sir. Okay, thank you, sir. Yes, fortunately for me, most of the other comments I have here are pointed out. In fact, if by the time the Professor our landlord hands over the corrected thesis to him, he has gone. Okay. And the other one that people have pointed out, I can go and relax and be rest assured that we have done, necessary work on your thesis. But I just want to take you through some practical.
Roman figure. Okay. Okay.
Can I go on, sir?
Okay.
Okay, I just want to take you through some practical understanding of some of your figures here, maybe one or two, to justify if you really understand as a material
Prof.
person. Yes, sir.
We want to increase your volume.
Okay, so I just want to take him through some practical understanding of some of the results he got as a material scientist. For example, if you go to, if perhaps you just discuss what you have, or maybe you give it a thorough analytical thinking of what the result actually speculates. For example, plate 4.2b, 4.2b, that is page 96, is EDS micrograph of the EBT phosphate ore as received. Can you see it? The EDS. Are we together? Are we together? Can you see it? Excuse me. I'm in a meeting. Hey, Joe. Okay. Meeting. Okay. Are you with me? Hello? 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 Can you hear me? Hello? Can you hear me? I'm not sure you can hear me. Exactly. I love that. Alone. My issue is that what I pay me the money more abuse.
We have a power failure as usual. So they are attending to it.
All right, sir. All right, sir.
Okay, sorry for that. Okay.
Hello, sir.
Hello, bro. We're online again.
Okay, change the same link. You know, you can join. Okay.
The same link.
Okay, let's join.
Okay. I don't think the equation doesn't mean it's correct. What I just told you now, I learned it during my